In this video, we will be solving exam number 2, part 1A, kinetics, and I'm Riley Bueller, and I will show you how I will approach this problem and solve it. So first, we are going to see the question is given here. We are told to rank the value of the indicated quantities from largest to smallest and provide a concise justification for each answer, which we will do by showing the math for this. And the three indicated quantities are the value of the rate constant with the correct units for the following reactions. Number one, a first order reaction done at 13.2 degrees Celsius, which when ln k versus 1 over t is graphed, gives a straight line with the equation y equals negative 0.3112x plus 1.01. And then second is a reaction that obeys zero order kinetics with an initial concentration of 1.22 molar and has a half-life of 1,110 seconds. And then the third quantity is a reaction that follows first order kinetics, which takes 892 seconds to go from an initial concentration of 0.452 molar to 0.0720 molar. And the way we're going to approach this problem is identify which order of reaction, first order, zero order, or second order, and then we will use equations given on this reference sheet and the quantities given in this problem in order to solve for the rate constants, and then we will compare them to each other. And we will do this by isolating 1, 2, and 3 individually. So first, we're given a first order reaction and we're given this equation. And we know when ln k versus 1 over t is graphed, this will give us a y equals mx plus b equation in this format. And this can also be found on the reference material right here. And we know that this relates to first order kinetics. So if we have this form of the equation and we're given this equation, I've identified where the k values will mirror each other, highlighted in blue. So then we can see that negative k in the skeleton of the equation, given in our reference sheet, is equal to 0.3112 in the equation given in the problem. Therefore, we can multiply both sides by -1, and we will get that the value of k for the first quantity is 0.3112, and the values will be 1 over seconds. This is because all first order kinetics, the rate constant is 1 over s, but we know this because this value times t, which is time in seconds, has to be neutral in a sense. So 1 over s times s will give us no units. And that's how we solve the first one. And we'll use 4 significant figures because we're only using this value. We're excluding this value of 3 sig figs because it was not involved in our calculation. Therefore, we will keep this at 4. For the second one, we're using zero order kinetics and we are given an initial concentration and the half-life time. And this equation we can find on our reference sheet here for zero order kinetics. And then if we go back, we can rearrange this equation by multiplying by 2k to now get this equation, and then divide both sides by 2 times the half-life, which is t, with a subscript of 1/2. That will isolate k on its own, as we see over here, and then the division that we just performed will be the denominator of this side. And now we're given these quantities, the initial concentration, which we can find if we scroll up right here, where it says initial concentration, and then the half-life is 1,110 seconds here. We'll plug those values into our equation and solve for k. First by multiplying these together and then dividing 1.22 by this number. We'll get a long number in our calculator, and we will round this to 3 significant figures because 3 significant figures is the minimum number of sig figs given in our equation. Therefore, we will get 5.50 times 10 to the minus 4 molar over seconds. And this is a similar reason as the first one because our k value is the one that is dividing the initial molarity. So molarity divided by molarity will cancel these, and then we want this as 1 over seconds in the bottom to bring it up to become seconds, so therefore our half-life will be in seconds as well. Finally, for our third one, we are given that it is first order kinetics, and we're given 2 concentrations and a time period. So we will use this equation right here, which relates to first order kinetics, and we're given an initial concentration, a final concentration, and a time. Therefore, we will plug these values into our equation here and solve just with common math, natural log of this value will give you this, natural log of this value will give you this. And then we'll just do some simple algebra by subtracting this from both sides, illustrated here, and dividing by this coefficient in front of k. And we will get that the value of k for this third quantity is 2.059 times 10 to the minus 3. And we'll round this to 3 significant figures because this is the minimum amount of sig figs given in our problem, and we'll have 2.06 times 10 to the minus 3, 1 over seconds. And this is for the exact same reason that I explained in the first one, and it also holds true for all first order kinetics rate constant values. Finally, we are going to go back to our problem, and we're going to rank the values from largest to smallest. So we have K1 is 0.3112, which is the greatest. And then we have, comparing these two, K2 is clearly the smallest because we have the smallest, or we have the greatest negative exponent. So that will be our smallest K value. And then K3 will be our middle value to give us a ranking of 1 is greater than 3, which is greater than 2. So we can see that approaching this problem involves breaking it down into 3 steps to find our first order reaction, our zero order reaction, our first order reaction, and use our reference table in order to find our values and then calculate our values of K with the given initial concentrations, final concentrations, and amount of time it takes for these processes to occur in order to find our K values.